Hi everyone, today's video is about momentum and impulse momentum theorem. The goal that accompanies this video is I'll be able to apply the impulse momentum theorem to find estimates of average forces during collisions. I apologize for the construction noise in this video. Momentum is a measure of how difficult it is to stop a moving object. It is a vector quantity and it is measured in kilograms times meters per second. So momentum is only present when an object is moving. If object has no velocity, there is no momentum, and it is different from inertia, what we learned in the previous chapter. Inertia is a property of a mass. It does not depend on the motion of the object, but momentum is the quantity that includes both mass and velocity. So there is another term, linear momentum. So when we're talking about momentum in this unit, we always think about linear momentum. In later chapters we'll talk about angular momentum for rotational motion. Let's look at this example. A bomber mass 3,600 kilograms departs from its aircraft carrier with a velocity of 85 meters per second due east. What is its momentum? In this example, we write down our variables, mass, velocity, and direction. Then we write the formula for momentum, mass times velocity, and we multiply the values and we calculate that momentum is 306,000 kilograms times meter per second, and it has a direction because it's a vector. There is another physical quantity that we're going to learn about today, and it's impulse. Impulse is a change in momentum. It's a final momentum minus initial momentum. It's represented by the letter capital J, not I, because letter I is taken by another quantity, which is the moment of inertia, which you will learn in another unit. And measured in newtons times second. There is no special unit for momentum or impulse. It's just the two units combined, newtons and seconds. So capital J equals change of momentum, or final momentum minus initial. So this equation is not on your reference table, so you need to memorize this equation. And let's look at the example. A 6-kilogram block sliding to the east across the horizontal frictionless surface with a moment of 30 kilograms meters per second strikes an obstacle. The obstacle exerts an impulse of 10 Newton seconds to the west on the block. Find the speed of the block after the collision. So pay attention here that the impulse also has a direction. It's a vector, so you have to pay attention to the directions here. So we wrote down our variables. The mass is 6, initial momentum 30, and the impulse is negative 10 because it's in the opposite direction. Let's find the final velocity. So let's write the equation for the impulse. It's the change of momentum, final minus initial, and we write the equation for the final, which is mass times final velocity, and we keep the momentum for the initial because it's given. Then we do some algebraic manipulations to find the final velocity, which is momentum with impulse plus initial momentum divided by the mass. And when we plug in the numbers, we use the negative sign for the impulse, and we calculate that the velocity final is going to be 0.56 meters per second east, which is positive. So the last topic we want to talk about today is the impulse momentum theorem. When an unbalanced force acts on an object for a period of time, a change in momentum is produced. That is the impulse momentum theorem. It's a very important theorem. The equation looks like delta P equals the force, the average force multiplied by the change of time, the time interval the force is applied, and the let's look at the example here. So we will be using the graphs for the first time graphs a lot to calculate the impulse or the change in momentum for this unit. So it is different from the graphs in previous unit, where you had force on the y-axis and distance on the x-axis for calculating work done on the object. So this x-axis represents time, so do not confuse those two type of graphs. So the area under a force time curve is equal to the impulse. So the force is the changing force in this situation, and the area under the curve in this situation will be equal to the change in momentum or impulse on the object. Let's look at the example. A tow truck applies the variable force of F of t equals 1000 t on a 2000 kilogram car for a period of 3 seconds. What is the magnitude of the change in the car's momentum? And if the car starts at rest, what will be its speed after 3 seconds? So we want to create a graph. This is the time axis measured in seconds, 1 to 3 seconds. We know that's how long the force was acting on the object, and this is the force measured in newtons. So in 1 second the force was 1000 newtons, in 2 seconds 2000, and in 3 seconds it's 3000 newtons. So we create this graph, and the area under the graph, this area of a triangle, will be the change of impulse. So we write down the formula, and we find the area of the impulse here, and the area is 1/2 height times the base, which is the area of a triangle right here. So it's 1/2 3 seconds times 3000 newtons, so it's 4500 newtons times seconds. And for finding the velocity, we can write that initial velocity was 0, the final was unknown, but we know the mass of the object, so we can find the velocity by knowing the change of momentum and the mass of the object. So we find the velocity by substituting the values, and the final velocity is equal to 2.25 meters per second right here. So please fill out the Google form, and thank you for watching.